everyone. I'm Andy JP Magtangog. My report is all about first law of thermodynamics. Let's go. Come with me and explore what is first law of thermodynamics. First law of thermodynamics. Let's read the objectives. By the end of the lesson, you should be able to define thermodynamics and explain its importance in understanding energy changes. State and describe the first law of thermodynamics and its significance in energy conservation. Explain the equation E equals Q plus W, identifying the roles of internal energy, heat, and work in a thermodynamic system. Differentiate between endothermic and exothermic processes and provide real-life examples. Before we begin, let's listen to LeBron James, the King.
Welcome to an exploration of energy and thermodynamics. We will discuss how energy is the fundamental capacity behind doing work and transferring heat. This introduction sets the stage for understanding how energy changes drive the world around us. Energy is the ability to do work and is involved in transferring heat between systems. It plays a crucial role in various processes, from powering engines to fueling natural phenomena. Recognizing the ways energy moves helps us grasp the behavior of matter. At the heart of our discussion is a simple yet powerful formula: energy equals heat plus work. This relationship shows that the energy change within a system can come from either heat transfer or work being done. The formula serves as a fundamental principle in thermodynamics. Digging deeper, the formula breaks down into two key components. The first term represents the change in the system's internal energy, which includes both kinetic and potential energy. The second term accounts for the heat energy added or removed. Together, these concepts allow us to predict and control energy changes in various processes.
Thank you, King. Now, let's define the first law of thermodynamics. The first law of thermodynamics, also known as the law of conservation of energy, states that energy cannot be created or destroyed. It can only be transformed from one form to another, as LeBron James said earlier. This principle is evident in everyday situations. For example, water can generate electricity. In a hydroelectric dam, potential energy of water is converted into kinetic energy as it flows downward. This kinetic energy rotates turbines, which then generate electricity. Second is, a biker converts kinetic energy into potential energy when pedaling uphill. When the bike moves downhill, the potential energy is converted back into kinetic energy. Energy is a fundamental entity in nature that can be transferred between different parts of matter. In simple terms, energy, or E, is the capacity to do work, or W, and transfer heat, Q, expressed mathematically as E equals Q plus W, just like LeBron said James earlier. Energy changes occur everywhere. For example, burning fuels releases energy. Boiling water or cooking food requires energy, and photosynthesis needs energy from the sun to take place. Understanding these energy changes is essential because they help us predict and control chemical reactions, which have many practical applications. Let's break down the formula. E equals Q plus W. E, or internal change energy. This represents the total change in a system's energy. It includes all kinetic and potential energy of particles in the system. Q, or heat transfer. This represents the heat energy added to or removed from the system. W, or work done. This represents the work done on or by the system. If W is positive, work is done on the system, for example, compressing a gas. If W is negative, work is done by the system, for example, gas expanding. Now let's do an example calculation. Suppose the system absorbs 200 joules of heat and does 50 joules of work on the surroundings, which means the system loses energy through work. Using the formula, energy equals heat plus work. Energy equals 200 joules plus negative 50 joules is equals to, let's write 150 joules. Let's move to the exothermic and endothermic reactions. Every chemical reactions involve either the absorption or release of energy. Breaking chemical bonds requires energy, while forming new bonds releases energy. Endothermic reactions absorbs energy from its surroundings. As a result, the temperature of reaction mixture decreases because energy from surrounding particles is used in the reaction. An exothermic reaction releases energy into the surroundings. This release of heat often increases the temperature of the reaction mixture, the reaction vessel, and even the surrounding air. It's an image that comparing the two. As I said earlier, or LeBron James said earlier, the first law of thermodynamics states that energy can't be created or destroyed, only transferred. This directly applies to endothermic and exothermic reaction. Endothermic reaction absorb heat, increasing the system's internal energy. The surroundings lose heat, often causing a temperature drop. Examples is melting ice, boiling water, and photosynthesis. While exothermic reactions release heat, decreasing the system's internal energy. The surroundings gain heat, often causing a temperature increase. Examples: burning fuel, condensation of steam, and combustion reactions. Summary is, if Q is positive, heat is added. It is known as endothermic process. If Q is negative, heat is lost. It's known as exothermic process. Thank you. Goodbye.